This is quiz 5 and this is on regularization. Question number 1. Let beta, which is beta naught and beta 1, be a hypothesis on the hypothesis hyperplane. If we choose a circle of radius d as the constraint equation g beta is given by. So we have these 4 options. Now beta is a vector. So this would just result in 2 times of beta. So this is not the right answer. This one is the right answer, as the equation of a circle is x square plus y square, which is equal to r square. So in that way, this is correct. And this one is also not correct, because this is again the same thing as the first option. This is addition of 2 vectors. And now the last one is correct, because this is a dot product, and the dot product of the vector with itself will be the square of the magnitude of the vector, and that is this is right. So beta, in our case, our beta vector is constrained and it is restricted to have this radius. So, and because of that, we know that the maximum magnitude that it can take is d. And so we have this answer, which is beta into beta equals beta times beta dot beta equals d squared. To consider the context of gradient descent based learning for linear regression, given below is the contour plot of the error function, where beta naught and beta 1 are the coefficients to be estimated. Let EA, EB, and EH represent the error values on the contour lines A, B, and H respectively. So we have A, B, C, D, which sort of go outwards from the optimal beta star. Right, so let beta star be the optimal coefficient minima learned from the gradient descent process. So this is not from regularization, but this is from the gradient descent process. So before regularization, choose the right expression for the relationship between the error values of the contour lines from the options given below. So if we draw these contour lines as equi-error surfaces on the z-axis, right? Depending on their error values, we know that from beta star is the minima, right? So, and then these contour lines, they go outwards, and for each contour line, the error increases. And therefore, we know that E beta is the lowest. And from there, EA, EB up to EJ, it increases from there. So this option is right. Next, on the hypothesis hyperplane, where each point beta is a hypothesis, the contour curve in blue of the error function E beta and the constraint circle in red tangentially touch each other at a point P. Given this statement, which of the following are true? Okay. Okay. So let's just draw the tangent line. So here I've drawn the tangent line, and let's go through these options. Now we know from the lecture that for any point P on the error surface or any curve, the direction of steepest ascent, or the gradient points directly perpendicular to the tangent from that point. So if this is a point, let me just, yeah. So so if this is a point and we have a curve like this, we know that it is directly pointing outwards, and it is always perpendicular to the curve at that point. So in that case, the first option, the tangent of the contour curve is parallel in direction to the gradient of the constraint circle. So actually the tangent for both these curves are the same line. So this is not true. The tangent of the contour curve is normal to the gradient of the constraint circle. Yeah, this is true. The gradient of the contour curve is parallel and opposite in direction to the gradient of the constraint circle. That is also true. We see that both of them must be pointing in the opposite direction, as the circle increases in the opposite direction to the to the error surface. This will be true for wherever the error surface may be. This would be true. So this is true. The gradient of the contour curve is normal to the gradient of the constraint circle. This is false. They are actually parallel and opposite in direction.
Next illustration.
So for that one, I think if you go back to the previous one, I think the second and the third were, oh, one was tangent and other is the gradient. Okay, got it.
Yeah, yeah. The parameter of a simple linear regression model, beta naught and beta 1, are plotted on the x and y axis respectively. On the base hypothesis plane, the error function E is plotted on the z-axis. The gradient vector of the function E at a point P on the hypothesis plane is, okay, so for this thing, we know that gradient vector, it actually just points, it has a magnitude and a direction, and it is a vector on the base hypothesis plane. That is its definition. um, but I guess a lot of people get confused between a tangent and the tangent here is just it's a plane. So let's say there is a point on the error surface. The tangent is the tangent plane is a plane that just touches that curve on that single point, and it doesn't touch anywhere else. So that is a tangent plane. But the gradient vector is a vector on the base hypothesis plane, and it points in the direction of the steepest ascent. So in whichever direction you will have to climb up the hill, that would be the direction. So it'll be like north, or it'll point in a direction plus some, it will have some magnitude which tells you the slope at that particular point. So in that case, this for this we know that it must be on the hypothesis plane, gradient vector. Given a differentiable function gx and the contour surface of this function, then the path of no change at a point on the contour surface is, okay, I think this could have been worded slightly differently. The path of no change in magnitude, or no change in the error function, I think that would be, or no change in the function would be appropriate. But what it basically means is that at this point, so now we consider these options. We look at the base hypothesis plane and we look at delta g. Sorry, we just look at the gradient. This is the function g, so we look at the gradient uh, at that point. So the first option is in the direction of nabla g. Saying it wrong. So it's nabla g. The direction of nabla g, that is not correct because that would be the path of steepest ascent. In the direction along the contour surface, well, that is true, because if we go along the contour surface, we will not see any change. In the direction of the vector k such that k dot nabla g equals 0. Now that is true because if we that would be directly perpendicular to this vector, and we know from the cosine property or rule that uh, when we have a dot product and it is the value is 0, we know that they are perpendicular to each other. So the two vectors are perpendicular to each other. So this one is also correct. And we have in the direction along the contour surface, in any arbitrary direction away from the contour surface, that is not true. And in the direction opposite to nabla g, and that would be the path of steepest descent. So let's just the next one. Given a differentiable function, so the same question, they're asking this path of steepest ascent. Steepest ascent is in the direction of nabla g. And the same question with the path of steepest descent, and that would be in the direction opposite to nabla g. So after the gradient descent learning process, if polynomial regression produces a very large optimal coefficient minima beta star, then so the mean squared error of the model with the coefficients beta star is very large. No, that may not be true. Um, on the hypothesis hyperplane, beta star is very close to the origin. That is not true. On the hypothesis hyperplane, beta star is very far from the origin. That is true. Almost everyone got this answer correct. The paraboloid error surface of the error function is far above the hypothesis hyperplane. This is the same as the first one. These both mean the same thing. That is not true. The gradient vector of a function g with parameters x and y at a point p equals a random point x comma y is given by. So we know that this point is on the input plane or the base plane of this function gxy. So now what is the gradient vector? It's just the partial differentiation of g with respect to x and then with respect to y. That and this is the vector. Okay, so we come to these really I really like these uh, illustrations made by Asif. So the figure below shows a unit circle of some arbitrary Minkowski norm. Which of the norms is the figure most likely to represent? Okay, so can anyone answer this? It's simple.
Half.
Yeah, half. So we went through this in class. If it's is concave, we know that it's less than 1, and as it gets convex, we know it goes greater than 1. So now this is 1, right? So this is the Manhattan distance. And a circle, and we know that it's 2, Euclidean distance norm. And the square. So now this is the most convex it can get, and so now that is Manhattan distance. Oh, okay, the answer is given as Manhattan distance, but that's not true.
And I think the label is incorrect, but L is
Yes,
equal to infinity. Yeah.
yes, okay.
Well,
I'll
I
change
told
this
Asif,
question.
I think, yeah, but I think
I think
we
the
can.
original round he kind of had Manhattan Euclidean mixed.
Okay,
Everyone looks at the L number anyway, so
yeah, okay. Even I didn't notice it until now. Okay, I'll change it. Yep. If we increase the regularization hyperparameter lambda of a regularized regression model, then during the gradient descent learning process, what happens to the size of the constraint? So this could be just understood. We could just think that as we increase the dampening um, of if, yeah, as we could increase the dampening, then the lambda increases. And when we increase the dampening, the size of the constraint region decreases. But I've also made a small illustration to kind of understand it visually. So we know that as we go further away from this bottom of the curve, the gradient increases quite rapidly. So if we look at these different contour surfaces of the error function and different constraint regions that we're selecting, there's this relationship between the optimal points that we would, so the A, B, C, D are the optimal beta stars that we would reach if we choose, say, this particular uh, yeah, if we choose this particular constraint circle, then we would arrive at A. If we choose this, then we'll arrive at B and C and D, so on. But we know that at this particular point, at say A, then nabla E is 0, but nabla G is quite large because this is compared to the other circles, the nabla G must be large because the circle is larger. And so we also know that nabla E equals minus lambda nabla G. And this is just a parameter that kind of makes these two equal. So in that case, equal and opposite. So um, in this case, lambda should be 0 so that they both will be equal, because nabla e is 0. And here at point B, we see that the error slowly increases. The gradient at BCD, they slowly increase, but for BCD, nabla G will definitely slowly decrease because the size of the constraint decreases. So in that case, if we just look at this relationship, we kind of see that lambda is likely to increase, because half times of nabla G, only that would be equal to nabla E. So these are just approximate. Obviously, this is just for understanding and they're not exact. Um, but we see that lambda is supposed to increase. And only then these nabla G and nabla E would be equal. So we see that as we decrease the size of the constraint, or we increase lambda, the size of the constraint decreases. And that's how pretty much I think how we control the size of the constraint, by setting a parameter, setting our lambda parameter.
Nice
So
illustration. The red constraint circles, yes.
yeah, the size of the constraint decreases. Now consider that on the hypothesis plane, the contour surface of the error function E with gradient nabla E and the constraint surface G with nabla G tangentially touch each other. Then, okay, the following relationship holds. So this is the relationship that we just saw. So what is this called? This is just to make sure that you know what it's called. It's called the Lagrange multiplier. After the gradient descent learning process, if polynomial regression produces a very large optimal coefficient minima beta star, then the model most likely overfits the data. No, that's true. We have a large quantity of data. That's not true. I mean, it could be, but that's not what we get from the question. The values of the variables are large, and we haven't standardized the variables before learning. So this was discussed in class, and I think Premjit raised this question. If you want, you can go back to the lecture and watch this again and understand why this is not true. The models most likely underfits the data. That is not true. Next. Okay, so we have to find the expression that shows the lasso regularization loss function. Okay, so can anyone answer this?
First, let's review that. Lasso is the
Yeah.
one that's not a circle, and it's the norm is L equal 1, right?
Is
Yep.
it C or? Oh
It
no,
is
actually,
plus.
Is it
it is
plus or
it is
minus?
B.
It's
It is B.
plus.
Yeah, B.
Yeah.
Yeah,
So
because
what we
adding
do
the
here,
regularization
yeah,
term. Yeah,
yeah, plus lambda delta
yeah,
H
plus
equals
lambda. Yeah.
0. This is what we want.
Mm-hmm.
And so that's why 2 is the right answer.
Also, that's in the textbook.
Yeah. Lasso regularization is superior to ridge regularization in making an accurate predictive model because, okay, um, we can't blatantly say that it's superior, because it might be superior sometimes. We might require, uh, you know, reducing, I mean, removing a few parameters, but we may not also need it. So dimensionality reduction, we might need that, but we might also not. So in that case, we cannot say that. Uh, what is the answer here? Lasso rocks. Lasso is more modern,
Cowboys.
and
None, I think. Yeah.
none of these. Yeah, none of these. Lasso is not necessarily superior to ridge.
Yeah, because Asif mentioned something about like NFL, like no
Mhm.
free lunch theorem.
Yeah,
Yeah.
yeah.
Exactly.
Which of the following is true? Okay. So what about the first one? That is not true. Minkowski norm L equals 1 is associated with lasso regularization. Yeah. Yeah, correct. And this is not true. L equals 2 is not true. That is also not true. Yeah, this one is true. It's because ridge is Euclidean space, and that is true. How is regularized regression different from ordinary least square regression? A regularized regression model includes a constraint term, the loss function, in addition to the sum squared errors, while the loss function of an ordinary least square regression model does not. This is true. Yeah. And the rest are not, because there's just one option correct. I'm not going to read everything. The ridge regularization loss function for polynomial regression of degree p is given by.
And ridge is L equal
Okay.
2, so you can think of
Yeah.
that to remember to square.
Right.
So that is C, I think.
Yeah. Correct. So, what is shrinkage in the context of regularization of a regression model? So, we know that shrinkage. Okay. So, shrinkage is the sample size. Shrinking the sample size of the data set, that is not true. Shrinking the training data set, also not true. Shrinking the hyperparameters of the model, that is not true. Shrinking the coefficient estimates and bringing them closer to zero. So that is true, because what we are doing here is, at this point the coefficients are quite large, and we are slowly, with our constraint circle, we are slowly bringing them, and we're shrinking them and getting them closer to zero. So that is true. Answers. Correct. What is the purpose of regularization? It helps mitigate underfitting. It helps mitigate overfitting. That is true. Yep. A point Pxy on a two-dimensional plane in vector notation is expressed as. So we remove these unit vectors, and we just use their coefficients, and this is how we represent a vector. The path of fastest ascent of a function is the direction along. So yeah, we're going back to this. It's along its contour line. That is not true. That is false. The presence of very large coefficient estimates of a polynomial regression model for a data set D tends to produce wild oscillations in the model's prediction curve. That is true, because each coefficient tries to pull the curve along its direction, and that results in a lot of oscillation. That is true.
You see the overfitting.
Yeah, you see the overfitting. The presence of very large coefficient estimates of a polynomial regression model for a dataset T signifies that the model may have significantly underfitted the data. So just as Kate said now, it has overfit the data. Same, and then we either should consider regularization or selecting a polynomial of lower degree. That is true, because we could either regularize, or we should think of reducing the hyperparameter. So true. Okay. My internet is slow. There's two more questions. Come on.
1 minute, you could do it.
Yeah. Come on. Okay. Yeah. If the regression model performs very poorly on the test data set compared to the training data set, it is likely that the model has overfit the data. Okay, let me read it again. If the regression model performs very poorly on the test data set compared to the training data set, yeah, this is true. Because the curve kind of hugs the errors as well, and it reads a lot into the noise instead of the actual signal. So, and that's why we see this. Okay, then if the regularization hyperparameter lambda is 0, for the same training data set, regularization, lasso regularization, ridge regression, sorry, ridge regularized regression model, lasso regularized regression model, and the unregularized regression model produce the same coefficient estimates. That is true because if in that case, the regularization term becomes 0 if lambda is 0. And so that is true. Yep. And we are done. Finish attempt and let's see how I did. Oh, I left off a few questions, but aha. Okay. Yeah, I think I did pretty well, except I didn't choose this answer. Yeah, otherwise it's fine. And I left out two
Nothing like
questions,
time
but I
pressure.
covered. Yep. And we're done.
Oh, very good.
Okay.
Right under the bell, just in time.
Yep. And let me stop sharing. Stop share. Hi, Asif.
Hi, Kyle. Thank you for holding this session. Kate, Kyle, Harini. This is really great. And did you folks, do you have any doubts? Are you guys finding the quizzes useful?
Useful for all levels.
Yeah, I'm asking the participants if how they think about it.
Yes, it's useful. Sure.
It is useful. So I have been experimenting with a different writing software called Sketchbook Pro. It will take me a little bit of time to get used to it. So today I'll still use OneNote, but I think we have hope. It might be a better thing to do, to use that. So we'll see. All right, so I should share my screen. Don't start recording yet. Let me situate myself properly. And where's my writing pen?
It's recording. I'll just ask Joel to cut it off.
Yes, sure.